Hello boys and girls. This is Professor Nelson from Electronics. Today we're going to talk about coils or inductors. This is a coil or inductor. And as you can see, in this case, it's made of enameled copper wire. We can see that it has several turns or coils. That is, a coil is made up of several turns. The coil's turns can be tightly connected, or they can be separated. To build a coil, you can use copper wire. It normally has to be enameled. This will prevent any contact between the coil's turns, otherwise it wouldn't be a coil. Or you can also use a more common wire. I'm talking about rigid UTP cable. You just need to find a cylinder of the required diameter to start making your coil. This here is one turn or a single turn. Now we can make a 2-turn, 3-turn coil. Here I have a fairly simple and straightforward coil. Now, to identify a coil, we have these 3 symbols, which are somewhat different from each other. That means they represent different types of coils. The first is an air core coil, which is the one I was showing you. This one here. It has an air core. It has nothing inside. And we could say that this one is also an air core coil, although I've already removed the core. Even so, this is an air core coil with nothing inside. We could say the same about this one. Just like this one here, since right now we have a huge coil with nothing like a core or center. After that we have the coils or inductors with iron core. You'll find iron core coils mostly used to generate a fairly strong magnetic field, as is the case with solenoid valves. In solenoid valves, they're used to open and close the passage of liquids or gases through pipes. You'll also find them in what would be relays. Here I have a relay, and this one has an iron core. And there's the coil. This coil has hundreds of turns. I couldn't tell you how many. Maybe it has thousands of turns, but in this case, it uses a fairly thin wire to generate a fairly strong magnetic field. And next to the core, help it to be able to move. In this case, this small tab to open and close the contacts. That's the case with iron core coils. In this type of coil, we're talking about a ferrite core coil. Ferrite core coils are most commonly used in power supplies. For example, this one here is a toroidal coil, but the core in this case is ferrite. The same is true of this board. This is a coil with a ferrite core. After that, we have this one here, from which I removed its core. It had its own core, which is this one here, in the shape of an L, which went in there. So it would also be a coil with a ferrite core. Now, coils are composed, as we mentioned, of several turns of copper wire. There can be coils with more turns, like this one, or fewer turns, like this one. And you might be wondering, how will this affect my coil? Well, to start, we need to know that coils have the Henry as their unit of measurement. Very similar to the case of capacitors, whose capacitance, or rather, their unit of measurement is the farad. In this case, it's in Henry, and like capacitors, coils store energy. In this case, let's see how they store that energy. But before that, we can observe here. Inductance, the property of coils to store energy in the form of a magnetic field, will depend in this case on this constant, which is the permeability of the core. Permeability is a property that indicates how easily the magnetic field created in a coil can pass from one end to the other. If we want to generate a magnetic field in any of the coils, it is necessary to energize them. In this case, we can energize them with a battery, that is, with direct current. When energized, a current will pass through each coil, and that will generate a magnetic field in each coil. And the sum of each coil will begin to generate a larger magnetic field, very similar to the following. Here I have a group of magnets. Imagine that each of them is a turn. Each of them has a force. However, when you have several of them in a row or in series, the force of all the magnets will add up. Therefore, this could be considered a single magnet, which has a much stronger magnetic field than an individual one. Therefore, if you energize the coil, it will generate a much larger magnetic field. This will be the sum of all the coils it has, generating a north pole on the positive side and a south pole on the negative side. The same is true for this one here. Now, in this case, it can also be energized with alternating current, meaning the coil can easily work with alternating current or direct current. That depends on what you want to do. Or it can also be a pulse signal, which is typically used in certain areas. Keep that in mind just in case. So, permeability means how easily these magnetic fields can pass from one end to the other. That is, how quickly they can pass. This is very similar to how current can flow through a conductor. If I have a copper conductor, the current can flow very easily. But if I have a lead or aluminum conductor, they aren't as good as copper. And because of that, it won't be able to conduct the current properly and will have losses, in this case, when current flows from one end to the other. Therefore, permeability would be the ease with which the magnetic field can pass from one end to the other. The greater the permeability, the greater the inductance of the coil as a whole in this case. Therefore, we said there were coils with air cores and coils with ferrite or iron cores. In this case, coils with air cores have very little inductance, and those with ferrite or iron cores have greater inductance. In other words, these ones here can store more energy than those with air cores. Well, that's in terms of permeability. Now, as for the N or number of turns, that's what we're talking about. The more turns it has, the greater the strength of the coil. For example, this one here has much more strength than if it only used 3 magnets or 3 coils. Then we have the area or cross-section of the coil. The area is in square meters just in case. That means how wide the coil is. That is, how big the coil is. This one, for example, has a specific area. This one, we can say, has a larger area. That is, how large the circle it encompasses. And this one has a larger area. Using this as an example, these are much smaller magnets, and these are much larger magnets. Now, which one is going to have more force or more inductance? In this case, the one with the larger area. This one here. The smaller one would have less force. Then, finally, we have the length of the coil, as mentioned above. The more turns, the greater the force. if we have a certain number of turns and these turns are completely close together. For example, as is the case with this coil, which has a fixed number of turns, which, if we compress them very tightly, the length from here to here would be what is indicated here. The shorter the length, the greater the inductance. The closer the coils are, the greater the inductance. However, if we move the coils farther apart, the magnetic fields of each turn will not be able to combine with the same force as the other turns we have. Therefore, it is important that the turns are tightly connected. That also depends on whether we want greater inductance. That's regarding the coils, or inductors. It's a way to achieve greater inductance. Okay, guys, let's use this circuit to observe how a coil can store energy, and how this energy can alter the signals we inject into the circuit. For example, we're going to use a power supply, a 5-volt power supply, but in this case, it's going to be pulsating so we can observe the changes in the signal when we place a coil in series with a resistor. The signals we're going to obtain are current and voltage. However, I can't obtain the current directly with the oscilloscope because it doesn't allow me to. However, I can obtain the voltage. Therefore, to determine the current graph, what we're going to do is measure right here, at this point. That is, we're going to measure the voltage across the resistor. This is practically the same as measuring the coil's current. So, let's see how the circuit works. First, let's focus on the current. Now, when we inject a voltage and go from 0 to positive, what will happen? The first thing is that the coils, in this case, react to the change in current. If the current doesn't change, the coil doesn't react. But in this case, there's a fairly intense change, going from 0 volts to 5 volts, and therefore, a fairly large current appears. Now, this is a coil made of copper wire. Copper wire has an intrinsic resistance, meaning we could say this coil has 1 ohm or 2 ohms of resistance. However, to those 2 ohms or 1 ohm, we'll add something called inductive reactance. This one is right here. Inductive reactance, in this case, is directly proportional to pi times the frequency and inductance, in this case the inductance of the coil. So, in this case, reactance means how the coil reacts to signals depending on their frequency. It's an additional resistance added to the intrinsic resistance of the material. As I said, if the coil is made of copper, like this one here, it will have very little resistance. But if you use a copper wire this thin, it will have a much higher resistance. So, inductive reactance is a resistance whose value will depend on the signal frequency, which will be added to the series resistance. That's what this graph generates. If you notice, when I add VCC, this signal doesn't become square, but rather generates a small curve. This deformation is caused by inductance. That is, the length of the curve will depend on the inductance of the coil, because this inductance will react and generate a reactance, that is, a greater resistance. Therefore, the coil behaves like a charging capacitor, more or less. At first, we can see that this has a high reactance. Why? Because it doesn't go directly to VCC, but instead gradually increases its value. This is voltage, but for us, it's going to be current. That is, as it increases, we can observe the following. Between this point and this point, you can see that the voltage is increasing. What does this mean? that the current here is gradually increasing. Because if it were a constant current, it would give us a different graph. However, it increased. It means there's an increase. An increase in what? Well, in the current. And if the current increases, what does it mean? That this coil is losing power. It loses power over time. That's mainly because a coil can store a certain amount of energy based on its capacity, and in this case, the coil would be about to fully charge. And once there's no change, precisely at that point, well, the voltage between this point and negative current or the resistance reaches its maximum. In this case, the coil lost its inductive reactance. It reacted at the moment of the change, tried to maintain it, but reached a point where the coil could no longer do anything. Now, however, when we move to a low pulse, which is what happens, the coil already has an already established and fixed magnetic field. However, when we want to go from positive to negative, the same thing happens. It turns out that the coil now behaves like a battery, and in this case, its energy is discharged into the resistance. This means that the resistance doesn't drop directly to zero, but rather gradually discharges. The current is initially high and decreases to the point where it delivers 0 volts. And the same thing happens again with the next signal. I hope this isn't confusing. The truth is, it is at first. Now let's see what happens with the voltage. Since it seems to me that voltage is a little simpler, well, I think so. In the case of voltage, we have this measurement precisely in the coil, not in the resistance. In this case, we use the resistance as an auxiliary element to obtain a graph of the current. In the case of voltage, we can take it directly from the coil. This works as follows. When we have the change from 0 to positive, what happens? First, I mentioned that the coil has a high inductive reactance. That is, a high resistance. Now tell me what happens if this one had 100 ohms, as an example. Because I haven't calculated anything, it's just an assumption. But it has a high reactance, and this one has 20 ohms. Which of the two has the highest voltage drop? Well, on the coil. So, initially, the voltage will be high. Or higher here than here. Therefore, when I measure with the oscilloscope, I'll see most of the voltage here. It would basically be VCC. Because the reactance is quite large, as long as we have a low-value resistor in series. Now, this reactance initially appears very high. Because there is a sudden change between 0 volts and VDC. But after a brief moment, this reactance begins to decay. As it decays, it means that this value is going down. In other words, it's no longer 100, but 90, but 80, and so it goes down and down. And how much do you think it will go down? To its intrinsic value, or the resistance of the coil. Remember, a coil has a resistance. Let's suppose it has 10 ohms. That will depend on the length, diameter, and the filament or wire being used. Then it will reach a value of 10 ohms. This shows this point here. In other words, this graph doesn't go all the way to 0, but that will depend on the resistance of the coil. That is, there's a small voltage that stays there. Remember, that small voltage is there due to the coil's resistance, which will inevitably remain a voltage. And another voltage will remain in the resistor. In this case, it would be the complement of this. It's a voltage divider. Now the interesting part comes later. When we go from VCC to GND, the coil has its magnetic field charged there, like a battery. Well, it turns out that when we cut off the power, this one here acquires a voltage. Let's assume it's the same voltage as the power supply. Only when that voltage is removed from the power supply, the coil, in this case, will supply the current. And when it supplies the current, it behaves like a battery. And when it behaves like a battery, batteries have voltage. The thing here is that before we had positive here and negative here. But when we remove the power, these polarities reverse. It becomes negative and then it becomes positive. This way we get this graph. Or because of this, we get this graph where you can see that the voltage reverses. And it does the same thing as in the opposite case. Its voltage begins to decay, in this case, generally to 0 volts. Therefore, the coil at that moment delivers its energy to the resistor. But this can be dangerous in some cases because they are sometimes not designed to withstand reverse voltages. Well, this is how a coil works. Thanks to inductive reactance and the coil's intrinsic resistance. I hope I didn't confuse them. Let's look at all this with the oscilloscope. Well, here we have the graph, and as you can see, it's identical to this one. We can see that we have a charge curve, and then a discharge curve. The coil practically prevents us from having a square signal like the original. This deformation is caused by the inductance of our coil. As I mentioned, if it has an air core, it will have a low inductance, but if we add a core, it will increase this inductance. And the inductance will directly generate a higher reactance. That is, higher inductance, higher reactance. For example, if we add this to the coil, the signal will change slightly. Let's see how much. You can see how the signal flattens. Now, the signal in this case is much more curved, taking the shape of a triangular signal, but slightly curved, meaning we no longer have a square signal. All this because we have more inductance. If I remove the core, the signal will try to become square again. So, with the core, we can change the inductance quite a bit, and in this way, we deform the signal. The signal will deform based on the inductance of the coil. Well, this as for the current. Let's now look at the voltage. There we have the voltage signal. The voltage is being measured directly at the coil. Right there on the coil. And that's why we have this reaction here. There we can see how the signal reacts to the reactance. This means that the coil has enormous resistance. And as time goes by, the resistance drops. In other words, the reactance decreases and reaches a point where there is a constant voltage. That constant voltage is caused by the voltage divider between the coil and the resistor in series. There will definitely be a voltage drop across the coil. Yes, because the coil has a resistance. However, when we put the core back in, let's see what happens. There we can see that in this case, the reactance lasts longer. It lasts longer because the signal doesn't decrease suddenly. This is because the coil stores more energy. This energy can be supplied or delivered for a longer time. It even lasts long enough to not even show the remaining voltage across the resistor, which is in series with our coil. Is one way of looking at it. And look at the negative part. It's the same thing I mentioned before. So here it delivers a negative voltage, and then that voltage decays because it's delivering its energy. The frequency I'm using, just in case for those who want to ask, is 10 kilohertz. So I'm working at 10 kilohertz. At lower frequencies, the reactance is different. Note that the formula says it depends on the frequency. The higher the frequency, the greater the reactance or resistance. So, This could go on much longer if we work at higher frequencies. The higher the frequency we're working with, the more this signal here might look like a square wave signal because the coil has quite a bit of energy. Okay guys, this is how the video ends. See you in the next video. Bye-bye.